Okay, part two. So here is our data recorded over 10 minutes. And you can see that there's a little bit of a latency and then there's a curve, and it doesn't really become linear until about the, well, putting my cursor here, at about the 3.3 minute mark. So my data in the first 3 minutes, I'm not really going to want to consider. Anyway, let's get into what we can do. So you can do all of the stuff as before. In my previous tutorial, you can find gradients and correlations, etc., etc. That's obviously in degrees Celsius per minute. We could do multiply M and C with this delta T, and then we've got energy per minute. If we divide it by power, we can get energy. So there's things we can do. But in this lesson, let's file export our data. Now, if we export it as a CSV file, we can then open it in Excel. So let me just save that, and we will open up the CSV file. And the great thing is it already labels all the headings. So, well, you know, I don't know what that A is there, but we can have a look at our data. In fact, if I just Control Z that, if I was to wrap text, we might be able to make it look a little bit prettier. But that's not why we are here. Now, I want to manipulate the data a little bit. First off, my time I want to be in seconds. So I'm just going to insert a column, and we'll just go seconds. I'm going to be quite rushed here. I'm going to go equals bracket that times 60, and we'll drag that down. Okay, so we want time in seconds because we're going to have the voltage was 10.6, the current was 3.4 amps, and we're going to find energy in just a moment. Now, what else do we want to insert next? Let's go energy. So, insert energy provided in joules. Again, I should wrap text so I can see what the heck's going on. I'm going to go equals bracket. Now, energy is going to be current times voltage times time. So I'm going to go 10.6 times, what happened to my 0.6? 10.6 times 3.4 times time, and I'm going to highlight my time column. So now we have the amount of temperature that's being provided over the 10 minutes. So at the end, I've provided 21,600 joules. Okay. Now our temperature probe, I don't believe it to be to that precision. It gave me to the nearest decimal, 1 decimal. So I'm just going to drop it down a little bit so it looks a bit prettier. Okay. Now, if I highlighted the whole data, I would get pretty much, oops, not that, I would get this curve. And as I said, I'm going to select from about 4 minutes. Okay. So when I get rid of him, when I highlight my data, I'm only going to be highlighting this and temperature and energy and temperature from 4 minutes onwards. Okay, so I want energy on the y-axis, and there's a reason for that. So we'll go insert chart, and we'll do a scatter, and we'll select the data by right-clicking, select data. I want my temperature to be on the x-axis, so we will add a series x values. I'm going to go from 4 minutes and the y values from 4 minutes also. So just be careful that you have highlighted the same range. You can check that by clicking on the data, and it will highlight the rows. Now, if I want to, I can drag these up, and I can drag these up. Okay, but again, you can see there was a reason why I chose not to, because there's a curve there. So I'm just going to look at, okay, Control Z does nothing. I would just want to look at this nice linear section. Okay. Now, again, in previous videos, I've looked at axis labels and scales and stuff, so I'm not going to worry about that. The main goal here is to add a trend line and obtain the gradient. So linear, and we want the equation, chuck the r squared there as well, press enter, go away, click on that, probably full screen as well. Okay, here we get 1,279. Okay, so what we have here, and I'm just going to write it off to the side, we have this in the form y equals mx plus c. And what we have here is that q equals some constant times delta t plus c. Well, we have an equation of q equals mc delta t. We're not really expecting a y-intercept. There will be a y-intercept on this because, actually, yeah, there is a y-intercept because, you know, we were at 20 degrees when we started, so this is kind of extrapolating it back a fair bit. Back to what I was saying. If I could just highlight the gradient, that should have said MC delta T. If I was to highlight this gradient, and it's not letting me, so I can't, but the gradient of my graph is going to be MC, okay? So now, if I also had mass equals 0.5 kg, I can now, from the gradient, I can say that gradient equals mass times c. Therefore, c is going to be equal to gradient divided by mass, which I could then say 1279 divided by 0.5. And therefore that is my specific heat capacity of the substance. Okay, so this was a nice little way of showing you how from a linear proportionality you can obtain information from the gradient. So we were able to put q equals some value times t. Well, that value is the gradient, which in our specific heat capacity equation is m times c. So if we can determine the gradient and we know the mass, then we're able to determine our unknown specific heat capacity. So this is how we might be able to get it by plotting linearized data. So hopefully you found this useful, and in future investigations or experiments you might wish to try and confirm your findings using Logger Pro. Now just be careful, at the moment we are still hand drawing graphs. So if you're doing a investigation or a prac that requires graphs, please be aware that you still have to hand draw your graph. You still have to determine the gradient by drawing in your rise and run and showing your calculation this way. Okay, you can still use Excel. You can provide the printed graph, but you still have to show you're working out hand drawing. Okay, so just treat this as a nice little useful tool to help you confirm your understanding. So hopefully you found this second part useful, and I will continue to make more of these as I think up more useful videos. So see you later.